Hello, this is exponential and logarithmic equation. So I know there is a note sheet here, obviously, that I'm showing you, and it's online, but I don't think this will be a tricky one to just write on paper. That should work just fine, and if I go too fast, you can always just pause it. So as far as equations, we have inverse properties and we have one-to-one properties. And inverse properties, you kind of already know these, we've talked about them a little bit. The inverse properties are that a to the log base a of x is equal to x, and log base a of a to the x also equals x. I showed you these the other day, I believe, with the triangles, and you can make the triangles again to show yourself if you would like, or you can ask me in class. The one-to-one properties are that a to the x equals a to the y if and only if, that's what that double arrow thing means, x is equal to y. And so a to some power equals a to some other power, even if only if the powers are the same. And log base a of x equals log base a of y if and only if x equals y. Same sort of thing. If two logs have the same base, those numbers have to be the same. So log base a of something, log base a of something, those somethings have to be the same, in this case, x and y. Strategies. So I'll talk over these briefly, but mostly I'll just show you. So first, you can rewrite so that you can use the one-to-one properties. So meaning you could use this one. So rewrite it in this sort of form. Sorry, these aren't one-to-one. That is my fault. I am highlighting the wrong things. So rewrite so that you can use this. So this is where you find the common base, or the common base here. So if you can write things in these forms, then you can set, your x equal to your y, depending on where it is. You can also rewrite an exponential equation in log form, or rewrite a log equation in exponential form, basically using your triangle. And so that's where if, let's say you know that log base 2 of x equals 3. You could rewrite this log base 2x, and the 3 would go right up here. And so then writing an exponential form, 2 cubed equals x. So 8 would be equal to x, so x would be 8. That's sort of what I'm talking about. So now we'll just go through and solve. So for our first one, we have our common base, e. So e to negative x squared equals e to the power of negative 3x minus 4. Since these are both e's, we can just set negative x squared equal to negative 3x minus 4. I'm going to move everything to the right because I want my x squared to be positive, and so I'll just add x squared, so I'll get x squared minus 3x plus 4 is equal to 0. And then I'll factor, so I'm looking, since a is 1 here, there's no number in front of the x squared, so it's an invisible 1. I'm looking for what adds to be negative 3 and multiplies to be 4. And so that's negative 4 and 1. So this factors into x minus 4 and x plus 1. You set x minus 4 equal to 0, you get x equals 4. You set x plus 1 equal to 0, you get x equals negative 1. So sometimes there's two solutions if you solve a certain type of quadratic. Next one. So 3 times 2 to the x equals 42. The first thing we want to do is try to get this by itself. So I'm going to divide by 3. So then I have 2 to the power of x equals 42 over 3, which is 14. Let's make a note over here to eliminate exponents. So if you see like a variable and an exponent, you don't want it to be there. So to eliminate exponents, you take the log or natural log, but typically log, of both sides of the equation. So something like this, 2 to the x equals 14, the x is kind of stuck up there. I'm just going to take the log of both sides. So then I have log of 2 to the x equals log 14. And the reason I did that, the reason it's helpful, is because then this x can come down to the front, and now it's no longer stuck up there in the exponent spot. So then x log 2 equals log 14, and then we can divide by log 2. So x is going to be log of 14 over log of 2. And if I ask you to, find a decimal approximation, you could just put that in your calculator and then round. Number 3, we've done problems like this before. So we're looking for a common base. So right now I have a 9 and a 27, and I can write both of those in terms of 3s. So I'm going to replace 9 with 3 squared. So it's like if the 9 was in parentheses, replacing with 3 squared, I have a 2x out here. 27 is the same as 3 cubed to the power of x plus 2. So now I have 3 to the 2 times 2x, which is 4x, equals 3 to the 3 times x plus 2, which is 3x plus 6. My bases are both 3, so I can set these exponents equal to each other. So 4x must equal 3x plus 6. Subtract 3x from both sides, and we get x equals 6. Natural log of x equals 2. So another note, to eliminate the natural log, exponentiate both sides. That's a fancy word for saying just do e to both sides. To eliminate e, take the natural log of both sides, or just ln both sides in terms of how we'll write it, but it means take the natural log of both sides. So this one here, natural log of x equals 2. I see a natural log, e on both sides. E and natural log are inverses of each other, so they cancel out. And so now we have x equals e to the second power, or e squared. Again, you could find what this is with your calculator, but we're not really worried about that right now. Or I'm not, so you don't need to be either. Next one. So since we have a log base 3 on both sides of the equation, and that's all we have, I can actually just set 5x minus 1 equal to x plus 7. I'm going to subtract x from both sides first. I don't care what order. So 4x minus 1 equals 7. Add 1. 4x equals 8. Divide by 4, and we get x equals 2. Next one. So I see a bunch of log 6s, which is great, but I also see that subtraction sign in the middle. So before I can really use any rules, I'm going to combine this left side, or condense it into a single log. So this is really log base 6 of 3x plus 14, leave enough space, 3x plus 14 over 5. So subtraction goes to division. And this equals log base 6 of 2x. And so now this works because all we have on both sides is log base 6 of something equals log base 6 of something else. So those insides must be equal. So 3x plus 14 over 5 must equal 2x. And then from here, we can multiply by 5 on both sides. So here we'll cancel out our 5. We get 3x plus 14. 2x times 5 is 10x. Subtract 3x from both sides. 14 equals 7x. Divide both sides by 7. So x equals 2, just like the 1, 2 above, which is a weird coincidence. Okay, number 7. Here, before we really can use anything, let's divide by 3. Yeah, if we have anything before our log or exponential function, or before our log, for example, like up here, when we had 3 times 2 to the x equals 42, we got rid of that 3, so it was being multiplied. by the exponential piece. If we have something multiplied by the log piece, same thing. So divide by 3. Now we have log base 3 of x minus 2 equals 4. And we'll have to use a different technique here because we don't have a log base 3 on both sides. So if we have a log just on one side, again, natural log or e is different because those cancel easily. With something like this, we'll make our triangle. And so log base 3 of x minus 2 equals 4. We could rewrite this and say 3 to the 4th equals x minus 2, right? 3 to the 4th equals x minus 2. 3 to the 4th is 81. So then x is 83. Next one, similar first step. I have a 5 in front of my natural log, so I cannot exponentiate until there's nothing in between the e and the natural log. So I'll divide by 5 first. And again, I want to show you what I mean. So if I had done the e here, there's a 5 like in between. It's kind of blocking the e from the natural log, so it won't work. So we divide by 5. Natural log of 4x equals 30 over 5, which is 6. So then we exponentiate both sides, cancels on the left. So 4x is equal to e to the power of 6. Divide by 4. So x is e to the 6th over 4, or 1/4 e to the 6th. I don't care which way you write it. Last example of this type. Now we have an e just on one side. We want to get rid of it. There isn't a number in front of the e, so if we natural log both sides, these are right next to each other, the natural log and the e, so they cancel. So 2x is equal to the natural log of 5 divided by 2. So x is equal to the natural log of 5 over 2. Okay, now we have kind of the only type of word problem we are going to deal with logs at this point. So we're investing $5,000, annual interest rate, compounded continuously. This means we use the PERT formula. So the PERT formula literally looks like PERT. So A equals PE to the RT. And for this, P is your principal amount. So what you start with, E is just E, right? It's just the number E, 2 point whatever. Then R is your rate as a decimal. And T is your time in years. So now we can actually do the problem. So A, well, that's what we're finding. So A equals 5,000, that's our principal, or what we start with. E to the 0.0675, so we take 6.75% and move 2 decimal places to the left, if that helps. And then T, so that's our general equation, and we want to know how long it'll take our investment to double. So how long will it take for 5,000 to turn into 10,000? So then 10,000, that's our A, equals 5,000 e to the 0.0675 t. Divide by 5,000, because we're trying to get the e by itself so we can natural log both sides. 10,000 over 5,000 is 1/2. Sorry, it's 2. So then we get e to the 0.0675 t. Now I'm going to take the natural log of that, and by that I mean both sides, but this e cancels. So I have the natural log of 2 equals 0.0675 t. And so if I divide by 0.0675, the time it will take for my investment to double is natural log of 2 over 0.0675. Calculator, and this is about 10.27 years. And that's it.